So a long time ago, there were two gentlemen, one by the name of Frank, and the other, his last name was Starling. So Frank and Starling, coming from two different countries. Frank was from Germany and Starling was from England, came up with a set of ideas that we still use today. And not just use, but actually are pretty relevant to how we think about how the heart works. And so these two guys, I just want to give a little shout out to both of them because they were leaders in their field 100 plus years ago, and their ideas are still very, very relevant to how we think about things today. So what they came up with, and this is kind of the content of the video, is related to pressure and volume. So let's start there. Let's talk about both pressure on this axis and volume on this axis. And you understand that P and V are pressure and volume. So if you increase pressure and volume over time, and let's say the heart is completely relaxed, right? You're going to get a curve that looks something like this, right? It's going to kind of go up near the end as you start really packing in the fluid. And we call this the end diastolic, that's where the ED comes from, pressure-volume relationship, ED-PVR. So this is kind of what the curve looks like. And I could take different points on this curve. I'm just going to kind of choose some points arbitrarily, let's say 3, 4, let's choose one up here, 5 points on this curve. And you realize that as you go up from point 1 through point 5, let's say this is point 1, 2, 3, 4, and 5. As you go from point 1 through point 5, your preload is going up. Remember that preload is related to pressure, and preload is really a sense for what is the stress on the walls. And of course, within the walls, you've got these little heart cells. So what's the stress on these heart cells? And we know that as the stress goes up, the heart cells themselves begin to really stretch out. And so I'm going to just kind of show that to you in this little diagram. You've got, let's say, this could be 1, this could be 3, and this could be 5, right? So this is kind of what's happening with heart cells as you go up, up, up in terms of the preload. They stretch out. So thinking about heart cells stretching out, and of course this is before they contract, what does this mean for contraction? And this is something that Frank and Starling thought about, and that's what I want to kind of jump into next. So just think about these 5 points, 1, 2, 3, 4, 5, and we're going to go kind of point by point through them each. So let's start with point 1. And here in point 1, you've got very little preload, right? Very, very little preload, and maybe it'll be useful to kind of just draw some myosin. So this will be our myosin. And I'll draw the myosin heads, drawing, let's say, about 20 or so on the bottom and on the top. So this is our myosin molecule in purple. And I want you to keep an eye on how many myosin heads are actually working. Kind of almost as if you're the taskmaster and you've got to make sure that the myosin heads are all working. Make sure you keep an eye on exactly how many are doing what we want them to do, which is contract or pull in the actin. So let me actually just take a little shortcut here so I don't have to keep redrawing this. And I'm going to move this down here, and I'll do it again, and I'll move it even lower. So we have our myosin there. Now, around the myosin, in fact, let me label it while I still can. This is our myosin, right? Around our myosin, we have, of course, actin. Let me write it bigger just so you can see it very clearly. We have actin, and actin is going to be, we'll do in red. But because we have at this point, almost a very low preload or almost no preload, I'm going to show you what that means for our molecules. You're going to have something like this, where you have everything kind of crowded together. And that's kind of the core issue I want to point out to you, is that you have lots of crowding problems. And of course, the myosin on the ends here, we've got, this is our Z disc. I'm going to write Z disc. And you have another Z disc here. And what I'm showing you is kind of a part of the sarcomere. Remember, the sarcomere is kind of the basic unit of contraction, and it usually goes from Z disc to Z disc. So this is just a part of it because you'd have many, many more actins and myosins stacked up and below it. But this is just to kind of give you a sense for what we're looking at, right? And this is, of course, our actin. So the question is, and I guess I should, sorry, before the question, let me throw in titin. This little green molecule is titin. So the question is, how or how would a contraction occur if you were to look at this scenario and you're kind of an inspector, you're just kind of assessing for problems? Would you expect that there would be any problems? Would you expect any problems here? And afterwards, I also want you to think about force. What kind of force do you expect to get out of this sort of arrangement? A lot of force or a little force? What do you think? Well, immediately I can see some problems, right? I mean, you know that the whole goal is to pull the z-disks in closer to each other. That's the whole point. Right? The myosin is going to yank on the actin ropes, you could think of it as a rope, and yank the z-disks in. And if there's really almost no space here, see this right here, there's almost no space here, it's all crowded, and this myosin is basically almost touching the z-disc, right? This guy right here is almost touching the z-disc already, so close. Well then, what do I really expect to happen? There's going to be almost no force, because the problem, I'm going to write it very clearly, is that the myosin is crowded. Myosin is crowded. Myosin is crowded, meaning it's right up against the z-disc right from the beginning. And that's a problem, right? Because that means that, what can you really hope to achieve if you've already gotten the myosin already against the z-disc? There's really no space for you to yank the actin in to bring the z-disc in closer. There's no space there. It's crowded. So I would say that's the biggest problem. And secondly, there's actually another problem here, and that's around actin, right? Because the actin has polarity, and this is an important issue, that these two actin molecules that I've kind of drawn arrows around are fundamentally different, right? Because there's a directionality to the way those proteins are laid out, and we call that polarity. So actin has polarity. And what that means is that then myosin can't simply reach up and grab the nearest actin. It has to grab the correct actin. So for example, these four right here, I'm going to draw them a circle around them in yellow. These four really want this actin on this side. And these four down here, they really want the actin on this side. But both of those groups of actins, or myosins rather, are blocked by the other actin. So for example, these four at the top are blocked by this segment right here, and these bottom four are being blocked by, I could actually change it, I could say these, or this segment right there. So there's actually some actin blocking going on. So I call that actin overlap or actin blocking. Overlap. Let's call it overlap because I think that makes a little bit more sense. So you've got some actin overlap, but that's kind of a secondary point here because the main issue is that myosin is just, frankly, it's just crowded. So in terms of force, would I expect any? I would say no, I wouldn't really expect any because there's really nothing for the myosin to really get done. There's just no space. Now let's say we stretch things out. This is scenario 2. So things are a little bit stretched out now, looking at our graph up above. Now things are stretched out, meaning that here, instead of the way it was drawn before, let me actually kind of correct it and draw it like this. You still have to consider the polarity issue, but things are a little bit more spaced out now, right? You've got something like that, and going on the other side, you've got something like, let's say, that. So look at this and now tell me what you think. You've got a couple of myosins that are still blocked, right? You still have a little bit of blockage here, right? These ones are blocked and these ones are blocked. And the main reason, again, for the blockage is that there's a polarity issue here and here, meaning that those myosins cannot simply bind whatever is closer, and they're really not able to get over to the side where the actin is, where they need to bind. So those 4 out of 20 myosin heads are not going to be able to work. But the rest of it is actually looking a lot better than before, right? We have some improvement. So here you've got some actin overlap issues. So in terms of problems, I would say actin overlap is still kind of an issue, right? And so in terms of force, I wouldn't say no anymore because now at least the myosin is crowded problem has gone away. It's not as crowded and there is room to move. So I would say I would expect some force. So when there is contraction, I would expect some force here. So things are definitely getting better, right? The stretching is helping things out because it's basically moving the actin so that it's not congesting the area, and the myosin is similarly moving away from the z-disc. Let me make a few more of these. I'll make one more, and we'll keep going. So now let's go to the third picture. Well, here, let's keep it up. Let's see what we can do if we keep the stretch going. Now I can say, well, gosh, I've got lots and lots of space for the myosin to work. So the very first point we talked about, that's a non-issue, completely non-issue now, because look at the titin. Watch as I draw the titin. Look at this. All those coils, all that space for the myosin to move, right? So the Z discs here, remember these are our Z discs, have a lot of room. If we really want to yank them in, we could really yank them in because the myosin is not right up against them anymore. And we've actually solved the other problem, the actin overlap problem, because there is no overlap at this point. Now you've really got nice spacing, and the actin isn't blocking the myosin from binding to another actin molecule. So in terms of problems, I would say no problems here. And in terms of force, I would say lots of force, because really I've got 20 myosin heads all ready to go, right? They're all pumped up and ready to do their thing, to bind the actin and to yank the Z discs in. So that was scenario 3. Now scenario 4 is going to be really, really similar, right? A lot of the same kinds of issues, because now I'm just kind of pulling a little bit further apart, and again, all those myosins are going to be able to work. They're going to have no problems of crowding. I've in fact even made more space out by the titin, so the Z discs are even further apart. So certainly all 20 myosins are going to be working, and I would expect no problems again. Really no problems here either. So in scenario 3 and 4, things are looking really good. And so of course I would expect lots of force. I would expect lots of force on this one as well. So it seems like, well, the more we stretch things out, the better things get. So let's just keep stretching. Let's just see how it goes. And let me just really stretch things out to the point where it looks almost like that. So you're thinking, well, wait a second, Rishi, I got a little too carried away here. And now, how the heck is this even going to stay put? Well, remember the titin is definitely going to keep my myosin attached to the Z disc, so that's good. So it won't just float away. It'll stay attached. But in terms of actually doing work, would I expect this to be a good setup? Well, I've really stretched things out, so there's no crowding issue. Well, that's true. But I have a new issue, right? Really, I have actin out of reach. Actin is out of reach. And if actin is out of reach of my myosin, then how the heck am I supposed to get work done? If they can't even attach themselves to the actin, then would I expect any force? I would say no. I would expect really no force, because it's just too stretched out. So this is kind of the overall look and feel of what happens as the preload goes up. As you get more and more stretched out, things seem to be getting better initially, but then they get a little bit too stretched out at the very end. And the optimal situation, this is pretty important, the optimal situation is really out of these five scenarios would basically be one of these two. So situation 3 and 4 are looking really good, right? Where we get lots of force, no crowding issues, no actin out of reach issues, no myosin actin overlap issues, nothing, right? It's just 3 and 4 are really our golden situations. And so just keep this in mind when you look at a preload curve, that it really does start affecting how well the myosin and actin are able to create force. And this idea of stretch relating to force is something that Frank and Starling thought of a long time ago.